Here. So we're going to change topics completely and talk about reionization, which is obviously connected to the CMB, although less than 60 years old. It's unclear exactly when Penzias and Wilson discovered the microwave background, but when I tried to research that, it's within 2 or 3 weeks of when I was born. So if you want to know what somebody that's as old as the CMB looks like, this is it. Anyway, we're going to start with Andrea Ferrara. All yours.
Yeah, good morning, everyone. So cosmic reionization is a fundamental process that is occurring throughout cosmic evolution. And it's particularly interesting because it connects galaxy formation, black hole formation, intergalactic medium, and also it has effects on the CMB, as we will see. So it's quite interesting. It provides unique information to inform the models. So recombination left the universe in a neutral state. It happened at redshift 1000, apart from some tiny fraction of relic electrons. And we had to wait for about 100 million years before the stars form and produce light in an otherwise dark universe as the CMB has shifted out of the visible range. So at redshift about 40, the first stars form out of primordial gas purely made by hydrogen and helium, so very different condition from present-day star formation, and started to produce ionizing photons that produce the inverse process of recombination, that is reionization. Reionization lasted for about 1 billion years, and it ended at redshift 6, therefore. After that, galaxies and clusters form, and this is the standard lambda CDM evolution. Now, the first stars form very early. Now, unfortunately, we cannot observe, we cannot access those distant epochs today, but we can rely on numerical simulations. And apparently, there is more or less a consensus that the first stars can form as early as redshift of 50. As you see here, in halos with masses of dark matter halos with mass of about 10 to the 5, 10 to the 6 solar masses, so very tiny subunits. And the structure of the gas that is falling into these dark matter halos is such that we have a core on top of which the envelope, the surrounding envelope, accretes and feeds the star, makes it larger and brighter. Now, so in this configuration in which you have a central core and an accreting envelope, you can compute by very simple physics the accretion rate onto that protostar. And it turns out to be very simple. So it's proportional to the cube of the sound speed divided by g. And so if you numerically estimate that number, you find that the accretion rate is about 10 to the minus 3, 10 to the minus 2 solar masses per year. This is 100 times larger than what we observe in present-day stars today. And so that has led to the agreement that because it takes only 70,000 years at that accretion rate to build the 300 solar mass stars, people that work in the field have now considered the fact the initial mass function of the stars could be top-heavy. That means that there are many more massive stars compared to the low-mass stars. And that, of course, has implications for the reionization because the stars are massive, they are hot, and they produce a lot of ionizing photons. So they are perfect for reionization. Now, these stars form within small galaxies, but as galaxies grow hierarchically and become larger and larger, and now we enter the time at which we can directly access these galaxies via JWST. Now, JWST has really, truly revolutionized the field, and in fact, only last week we discovered a new galaxy at redshift 14.4, which is the most distant one, and this is the spectrum. To me, it looks like, when I was young, there was a spectrum of redshift 0.5 galaxy. Now it's redshift about 14.4. And you see that there are also emission lines here, a very prominent one. That means that this galaxy, in spite of being so early, this is about 200 million years from the Big Bang, in spite of that, there is already a lot of things going on. So heavy element production, we see carbon, nitrogen, oxygen lines. So this is truly amazing. Now, with this in mind, for reionization, what matters is this quantity, an ion of Z. This is the ionization photon rate as a function of redshift produced by first stars and first galaxies, okay? So now this ionization rate is the product of three quantities. The first is the UV luminosity of galaxies as a function of redshift that can be constrained by the luminosity functions, as I explain in a second. Then the conversion of that UV luminosity into ionizing photon, and that depends on the initial mass function that I was mentioning before. And finally, the escape fraction of ionizing photons, so how many of the photons that you produce can really escape from the galaxy into the IGM and produce reionization. Now, let's start to analyze this first term here, and this is where we have made incredible advances thanks to JW. This is the new data on the UV luminosity function, so the number of galaxies per unit magnitude, UV magnitude, measured at different redshifts. Here is redshift 11 and 12, and we see that clearly there is a good agreement between models and the data, in spite of the fact that we have found more bright and blue galaxies than we were expecting before. But, you know, the physical explanation is still within the reach of many models, I should say. So we have a good agreement. Now, the challenge and the trouble start when you go to even higher redshift. And this is I'm trying to explain what the problem is. Now, what I'm doing here, I'm showing the luminosity density, the quantity that entered in the reionization rate equation, which is essentially the integral of the luminosity function. So we get one number at one redshift, and so these are the data points here. And these are the model, the red curve is the model that was fitting very well the data, redshift 10, 11, 12. And in fact, you see that the points here go very well on top of the red curve. But then, last month, essentially, there's been a claim of 9 ultra-early galaxy candidates. There are 6 at redshift 17 and 3 at redshift 25. And so now we have been, you see that the luminosity function, if these galaxies are real, remains very flat. And so we have been talking about tensions in the early part of the morning, but this is a phenomenal breakdown. It's not a tension, because the models would go down here, okay? So it would be orders of magnitude. If one of these galaxies is real, we have a discrepancy of about 4 to 5 orders of magnitude. So clearly, if star formation rate decays so rapidly, you can try to tune or to produce extreme models, to push your models at limit, and then you get into these red curves, the green curves, but as you see, you're losing then the agreement with the lower redshift data. So this is not a solution. So we are really in trouble, and so what is the possible alternative to explain this? Well, it has been proposed, I don't see it. It has been proposed that this galaxy can be powered rather than by stars, by primordial black holes. And of course, these black holes have to form before the stars, because they were there in place before the bulk of the galaxy population appeared. And so this is a possibility that we are currently exploring, and it's very interesting because also PBHs are interesting from the cosmological point of view. Now, from the topology of reionization, what we know is that we have to perform simulations, including radiative transfer, to follow the propagation of these ionizing photons. And so typically, you see here a map of the neutral hydrogen and the blue, how do I go? I can't show the, let me start again, sorry. You will see the bubbles around the sources that are the blue holes in the movie. These are the ionized regions around the first galaxies and first stars. And so there, the neutral hydrogen is ionized again, and so the intergalactic medium returns to be ionized. And so as it becomes ionized, then the visibility of the distant sources increases. So these bubbles grow inside and merge to each other. It's a percolation problem in physics. And so at the end of the day, the universe gets fully ionized by the radiation from the stars. Okay, so it becomes transparent. Good, so I don't need to explain what the electron scattering optical depth is to this audience, but just let me recall that it grows like 1 plus z to the 3/2, and that is clearly a feature that helps constraining cosmic reionization. Now, reionization affects CMB in 3 ways. There will be the next talk by Marina that will go into more details on that, but essentially they dump primary anisotropies on all scales. They produce small-scale secondary anisotropies and, of course, produce the polarization signal that we have discussed already these days. These are the beautiful polarization maps by Planck, and this is the spectrum. You see that reionization affects the EE and TE angular power spectrum at large modes, and from that we can obtain the value of the optical depth, which is 5.6%, implying that the midpoint of reionization, where the ionization fraction was 50%, is about redshift 7.82. Now, with all this, what can we learn? Can we use reionization to learn about the early galaxy population? Yes, because we can also, in addition to the CMB, we can also use the Gunn-Peterson effect, the fact that the distant sources located either when the when the IgM was neutral or when it is ionized show a different imprint in the spectrum. Low redshift, you see a Lyman alpha forest absorption, and then becomes patchy, and then finally it's a black trough of the Gunn-Peterson. Using this technique and using distant quasars in galaxies now, we can we can determine exactly what is the neutral fraction of the IgN in a different redshift. So you see that the quasar spectrum, which are the black lines here, can be fitted by the intrinsic spectrum plus absorption by the IgM. And by that technique, we can obtain the neutral hydrogen fraction. So to putting everything together, this is the evolution of the neutral hydrogen fraction as a function of redshift. So these are all the data points obtained from Gunn-Peterson and CMB. And on top here, we also have the optical depth determined by Planck. The blue curve is the model that we call it the fiducial lambda standard lambda CDM model, in which, however, the luminosity function drops too fast. The luminosity density drops too fast with redshift, so we are not happy with that. If we now say that these redshift 25 galaxies are real, and therefore we need some other source, then you get the orange curve. Now, you may think that the difference is very small, but cannot be neglected for 2 reasons. First of all, because it fits slightly better the optical depth value, but even most importantly, because thanks to the JWST, for this galaxy, which is a famous one for which you had the best ever spectrum of super early galaxy, it's called GNZ11 at redshift 10.6. Then what you have is just that this is an upper limit. So you see that the fiducial value cannot, produces a universe which is too neutral with respect to what we observe. But if you allow these early sources to be real and perhaps powered by PBH, but that I don't know, then you get a better fit. So this is something that we have learned. We have also, thanks to JWST, we also learned about the escape fraction, but this is a different story. So there are open questions because not everything has been sorted out, in particular when reionization starts and what is the role of pop-3 stars, improve radiation transfer, improve the understanding of escape fraction UV photo. So there's much work to be done, but this is my wish.
Perfect timing. Marina?
Okay, just going back to the impact of reionization on the CMB. And I mean, these newly freed electrons now are out there and can interact with CMB photons, and this will have an impact on the CMB, as anticipated by Andrea, an impact both on temperature anisotropies and on polarization. On temperature anisotropies, there will be also the generation of a new secondary anisotropy in the form of the kinetic Sunyaev-Zeldovich effect. The main parameter, as already said, that will control the impact is tau, the optical depth to reionization, and currently this is the least constraint parameter in lambda CDM, 10% constraint. So first impact, damping of CMB temperature anisotropies on small angular scales. And this effect is, of course, degenerate with the effect of other cosmological parameters, most notably AS, so the overall amplitude of perturbation. And in fact, with a CMB temperature power spectrum like the one from Planck, with 7 peaks measured with high signal to noise, cosmic variance limit measurements up to multiple of 1600s, what you really nail down is the combination AS, e to the minus 2 tau, at sub% precision when you analyze only temperature data. That's the quantity that you nail down. Then, with Planck, it was also possible to measure CMB lensing. Later today, Anthony will talk about this. If you account for this, which is a clean probe of the clustering of matter integrated along the time, along the photon path, well, then you can break this degeneracy and get a constraint from temperature and gravitational lensing. From CMB data, this one on the right are Planck 2018 results, actually. And nowadays we have lensing reconstruction, for example, by ACT, which reached a comparable significance over a broad fraction of sky. And then we have polarization, actually. Polarization, the impact will be on one end, the damping of polarization on small angular scales, very much like what happens to the temperature part, and on the large angular scales, there will be generation of new polarization signal. And this will result in a bump in the spectra, so location of the bump will tell you when reionization happened, because it's connected to the horizon size of the reionization epoch. Amplitude will be a direct measurement of tau, with very little dependence on other cosmological parameters, and the shape will have some mild dependence on the actual history of reionization. Planck spectra there on the left, and well, of course, if you put in, you add in to what we had before, so temperature plus lensing, and now we add IL polarization, you shrink a bit, is the blue curve, but it's really because polarization is going to break in degeneracies with other parameters. The game changer is the large scale angular polarization, and the posterior connected to that, you see in green in the plot. And as I was mentioning, large-scale polarization is quite a clean probe of tau, But on the other hand, as yesterday was commented abundantly, making these measurements of large-scale polarization is challenging. Signal is weak. Measuring those scales, large scales, those are better measured from space. And systematic effects, noise, foregrounds, are not negligible at all, have a big impact, in fact. And you need to be able to clean foregrounds, so need possibly broad frequency range for your measurements. You need end-to-end simulation, we learned that are as realistic as possible and that describe the interplay, the complex interplay between foregrounds, instrumental effects, and different data analysis techniques to ensure robustness of your results, because it's not simple to analyze this complex data. Okay, with Planck it has been possible, as yesterday Jaloub commented a lot, to do a lot of consistency tests internally with Planck, within Planck, thinking about different template for cleaning, different sky fractions, removing single multiples from the analysis to check the impact of every single multiple that is contributing to this, because at the end of the day this is a measurement to which only few tens of multiples really contribute. Also, complementarity with the LFI measurements with respect to the HFI, that is what I was showing in my previous slide. And in this case, it's it's a different frequency. The central frequency is different. With LFI, we use 70 gigahertz as a CMB channel, and then we use 30 to clean the synchrotron and 353 to clean the dust. And then we have also an overall estimate of tau from the low frequencies, combining LFI and WMAP. That's the blue curve on the left plot. And we built that once we have verified that actually LFI and WMAP data were in agreement. We performed consistency checks. You can see on the right there is the posterior for LFI minus WMAP, which is consistent with 0. Within errors, this means that the two see the same signal. And you can see these are all quite in good agreement, all these estimates. There is ZLOROR2 also, that Jaloub mentioned yesterday, the work from Pagano et al. And they are all very consistent there. And they all point to, let's say, a low value of tau. Low with respect to what? To first estimates. Just reminding the tau value from WMAP 2003, which is out of this plot, because it would be out of this plot in this scale. And then a trend to get to lower values. There is WMAP 9 on top there. The second point in green is actually a Planck analysis in which we used for the polarization, the WMAP polarization, but this time cleaned with the 353 from Planck, and this induced a shift itself. And then you can see other reanalysis, all quite consistent with each other, down to Planck 2020. I mentioned also some other estimates out of the plot, which were not in this plot. Roger et al., they investigated different type of likelihoods approach, because, as I said, when you have to analyze data that are noisy with systematic effects, you want to check every bit of the pipeline. And then Wolfs et al., 2023, neural networks applied to this. Beyond Planck, we heard about it yesterday, a reanalysis of WMAP and LFI all together, and still we get a value that is compatible with what we were getting. And this was mentioned also yesterday, a first measurement from class in cross-correlation with Planck. And what to look forward to? Well, LightBird, in this picture, will provide a cosmic variance measurements of E modes in a range of multiples that go from 2 to 200, say. And adding the information from the E modes from LightBird can allow you to get a tau estimate that is signal dominated. The value of the sigma associated to it will depend on the actual F sky you can reach, and this will depend on your component separation. We are targeting F sky of 70 or more, and this will reflect in a sigma tau that is what people call cosmic variance limit of 0.002, that in the plot on the left would correspond to the gray band that you see, vertical gray band. And now actually, when you get to this level of sensitivity, you might wonder whether you have sensitivity, an impact on tau, on the reionization history that you actually use in your analysis, and this is under investigation now within LIGHTBIRD. For Planck, this was not the case, as tau estimates were showing little sensitivity to the actual history of reionization that was adopted. There was an analysis that used a generalized a method that would fit any arbitrary history, using reionization history, using non-parametric models, and this is you can see it in the right plot here, is the blue curve, the one reconstructed for an arbitrary ionization history to be compared with the black one, that is the usual one, what we call instantaneous reionization, say, the tan-H model. And you can see that the blue one doesn't go far from that. It's got an heavier tail at higher Z, but the contribution to tau from that tail is given there at 95% confidence level and is not that strong. And several analyses in the literature so far of the Planck data have confirmed this picture. So another imprint we mentioned before is kinetic Sunyaev-Zeldovich effect, a secondary anisotropy generated by the scattering of photons, of CMB photons, of electron moving in bulk flows. This gives rise to a Doppler effect that will give rise to this signal, the KZ, that is composed of two components, an homogeneous part that pertains to the phase in which the universe has now completely reionized, and a patchy part that actually capture the scattering of bubbles that have a proper motion during the reionization phase. This will show up as an anisotropy, as we said, on very small angular scales. I'm just mentioning one measurement from the SPT here. This will contribute to very small angular scales, so very high multiples. And in this spectra that you see here for the SPT, in the SPT data, the points are the actual measurements, and then you see in red there is the primary CMB contribution that falls down very rapidly, and everything that you have above 3000 is really a combination of this SZ effects and extragalactic foregrounds. So dusty star forming galaxies, radio galaxies. And then you can exploit the different frequency dependence of these components to actually hope to separate them. And the SPT collaboration reported detection of the KZ for the first time at a 3 sigma level. Actually, the significance will depend some on the assumption that are made on the modeling of the other foregrounds. And then they attempt a constraint on the patchy component of this signal, assuming some homogeneous contribution based on simulations. And you can see down in the slide what's their upper limit for the signal at a multiple of 3000, and then the correspondent constraint on the duration of the reionization, as you expect the amplitude of the signal to be connected really to the duration of the signal, of the reionization phase. Just stressing again a point that Tau is important to learn about the reionization phase of the universe, but as we said, it might be owing to degeneracies with other cosmological parameters, getting a good measurements and solid measurements of tau is important also to constrain other parameters, and most notably the sum of neutrino masses. Tomorrow there will be dedicated talks about how to constrain fundamental physics with CMB. Assuming to get the value of the uncertainty on tau that I showed you before with the light bird, this is the type of improvement that you can get on the estimate of the sum of neutrino masses when you substitute, say, a prior that is informed by Planck constraint on tau with a prior with this 0.002 constraint. And you can see that you get an uncertainty on the sum of the neutrino masses, expected uncertainty at the level of 12 millielectron volt. This would allow, say, a 5 sigma detection of a minimum value in normal ordering for the sum of neutrino masses. So tau important for reionization, not just about that. I had another slide that, okay, just to close up with a few points, maybe useful for discussion later. So the Planck estimate of tau is going to be the best we have for quite some time still. Lightbird has the potential to give the best measurement, the most accurate measurement of tau from CMB alone. Synergies, complementarities with what JWST, Euclid, and then radio soon enough observation will be providing is probably key here, in the sense that joint analysis, feeding information on the ionization history in the pipeline, and joint constraint with CMB might be the key even to get lower to the 0.002 sigma tau that we mentioned before. KZ, can we do any better? Discussion later, probably. And CMB spectral distortion, we will know tomorrow, I guess. So that's everything from me. Thanks.
Thanks, Marina. Also keeping to time, excellent. So now we lastly learned more about the SZ effect from Salim Zaroubi. That's a joke, but by the way, just in case.
I smiled, Douglas. Hi, everyone. Thank you for the invitation. I'll wait for the talk. So I'll talk about another angle of, a different angle of probing the epoch of reionization, and that's the 21 centimeter angle. We are in a situation of probably pre-COBE kind of analogy of the CMB. We haven't detected anything. We are detecting. Sometimes we claim that we detected something and that we regret it, and we are, posing upper limits so far. But there's a rapid improvement in the field. So there are kind of three epochs that people talk about. I will not talk about the 21 centimeter itself because you probably know it. In terms of physics of it. So there are three epochs that people talk about when we talk about the 21 centimeter. First is the dark ages, when the spin temperature is coupled to the gas temperature, which cools adiabatically after it kind of leaves, decouples from the CMB, and it becomes very cold. So there's this absorption feature, which is not in this plot. However, so this is a purely cosmological effect that hopefully we will be able to probe once we go to the moon. It's impossible to do it from Earth because of the ionosphere. The second effect, which happens later, called the cosmic dawn. Cosmic dawn is due to the kind of formation of the first sources that start coupling the 21 centimeter spin temperature again to the gas and cooling it. But while these first objects are forming, they also start forming X-ray radiation that heats the gas. So you see it. So you see it in this phase. You go from outside of this, there are the dark ages. Then the dark ages kind of end with the spin temperature going back to the CMB. But then in the cosmic dawn, they veer again, and it's an absorption feature because gas is much, much colder than the CMB. Adiabatic gas expansion cools the gas much more efficiently than the CMB kind of drop in the energy as a function of redshift. But once X-ray heating starts kicking in, the cosmic dawn signature goes up in temperature and until it saturates during the epoch of reionization, when ionization also becomes very important. So these are the three features that we talk about, and this is a very complicated equation that we are trying to measure. Basically, what we measure is called the brightness temperature, or more accurately, the differential brightness temperature, which takes the difference between the 21 centimeter temperature, basically, and the CMB temperature. So the scale is about 28 millikelvin. That's the scale. We know our scale. That's unlike the CMB, which didn't know the Kobe fluctuations before, the scale of the fluctuations before. Here we know roughly, which is tiny. In this, these are very low frequencies. So we are going to frequencies of 100 megahertz and below, a little bit up. So this is a tiny, tiny, tiny signal. It's proportional to the density, 1 plus delta. It's proportional to the neutral fraction. It's proportional also to this interplay between the CMB and the 21 centimeter spin temperature and a bunch of cosmological things. So it's a very kind of complicated equation, but on the other hand, it's very kind of, it's different terms here become important at different redshifts, and we learn about a lot from here. When we talk about the epoch of reionization, this term is not important because the spin temperature is coupled to the gas, and gas at redshifts lower than 10 is expected to be already very hot. So basically, we are probing these two things, the ionization fraction, which is a field. It's a point that changes from it's a quantity that changes from a point to the next, and the density field. So these, as I say here, they teach us about cosmology, and this one teaches about astrophysics. It's a very rich kind of thing. These are the three epochs that I talked about. Yeah, I'm not sure if you see the dark ages, and so that's the feature. That's the cosmological feature, which is wonderful. If we get this, will we get more information than CMB, actually, if we get this, because it's many, 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 many redshifts and many kind of layers. But this is I don't think it will happen for the coming couple of decades, although we are going back to the moon rapidly, so it might happen, but don't hold your breath. This is the cosmic dawn, and that's the epoch of reionization. And so we are focusing on here. The reason we are focusing on the smallest signal is that just simply because it's very difficult to go to lower redshifts. So the lower frequencies. So this is the frequency range we are talking about. It's horrendously small. Okay, so there are two types of experiments in this game. One is called global detection, where you put a detector and look at the sky, and each frequency you get 1 point, and that's your measurement. So this is cheap because you have one detector. You have to do it very, very, very carefully and very kind of well. But then you get a result. So this is the EDGES result, which you are all familiar with. They detected the temperature, again, the brightness temperature, which is basically the intensity, a shorthand for the intensity of the radiation, as a function of frequency. And then they fit a kind of a smooth function, and from this, they saw this feature, which is basically doesn't fit anything we know. This is very low frequency, so I'll go back. So this is supposed to be in this frequency range. So this is cosmic dawn stuff. And the amplitude of this, the depth of this, is much bigger than anything we expected. So people got very excited. Maybe there's a new physics. Maybe the gas. The only thing that can drive the gas temperature so low is if it's coupled to the CMB, to the dark matter. So that's one of the options. Or you have excess of radio emission at these redshifts that gives you this contrast. And people got excited and started drawing all kinds of conclusions from this. And indeed, if this is accurate, it is a very big deal. However, there's always the danger that you are dealing with systematic. The problem was understanding what the systematic is. So there were many critiques on this, but the main one that actually turned out to be probably the correct one was that the instrument didn't deal well with the ground plane effects, the kind of how the absorption and reflection from the ground changes as a function of depth. And in this paper, I think Bradley et al., they just looked at the trees, at the kind of grass here or whatever vegetation that is here, and they concluded there's water down there. So there's probably a layer of water, and that affects things quite a lot. So an Indian experiment called SARAS, in its third version, to overcome this, they put their instrument on a lake, a very deep lake that's quiet. So there is no change in the properties of the ground plane as you go in depth. You can model them accurately, and actually they rule out finding anything down to 2 sigma level. So the edges result has not been ruled out completely, but it is ruled out for 2 sigma level. I think this is my feeling. This is the last word on this, but I must be honest, and the edges team is still insisting that this is not solving their problem. So there is a space there, but all the indications from at least this type of experiment is not pushing towards that. The other type of instruments, which is the more expensive, the more elaborate, the more difficult, is having interferometers. And there has been a kind of a flurry of instruments that have been kind of built specifically to look for the EOR and maybe cosmic dawn. The oldest of those is LOFAR, which I'm involved in. We started 20 years ago. So again, there's a kind of a comparability with the CMB history here. 5, okay, I'll try. And MWA, which is in Western Australia. Nenofar is a kind of spin-off of LOFAR, which is based in France. Actually, it's a big station that produces a lot of nice results, and it's geared toward redshift 16 to 23. And others here is SKA and HERA, which I will mention, mostly HERA I'll mention in the coming few plots. This is a very, very difficult game. We have been in this for 20 years for very good reason. There's lots, the foregrounds are formidable. The systematics are just really a nightmare. But we are making a good progress so we are working in the last 20 years, at least specifically in the last 15 years since we had the data first, and trying to improve our results bit by bit. There's a long list of candidates of difficulty that we can should address, and we have addressed most of them by now. I can talk a lot about why is this so difficult, but it's basically because you have a dipole kind of detector which has a polarized response. Your signal is not polarized, but it has foregrounds like the galactic foreground, synchrotron from the galaxy, that is polarized. So any kind of lack of calibration will leak the foregrounds into your measurement, and it will kill you basically in terms of, so we have been trying to take this under control. There's a way to kind of separate the foregrounds in a kind of schematic way. So I'll skip this, but I'll talk about the right-hand side of this slide. I don't have so much time. It turns out if you put the kind of the power spectrum as a function of k parallel, along the line of sight versus k perpendicular, which is across the sky, you can separate the power spectrum into 3 different regions. There is intrinsic foregrounds. There's foregrounds wedge, which is due to the fact that with different wavelengths, you have different resolutions, right? And that basically gives you not a straight line, but something that goes like in the angle. So your horizon is in that direction. And above that is the AOR direction, is the AOR region. So in principle, if you have this type of thing and you go to the AOR region, you should get to the AOR immediately. The problem, there is lots of leakage. So this is a good way to understand the problem. It's not a good way to apply it practically into data. So in LOFAR, we had a number of windows. I'll focus on two of these windows. Last year, we've published a few results, 3 results, actually, upper limits, which is incredible after being quiet for so long. So this is 2024. It's the red stuff. We published 3 redshifts, and these are the upper limits that we find, which has been a huge improvement. If you look at redshift 9, this is the same data that was analyzed in a better way. Our problem is that we detect upper limits, but they are above the noise. So when you detect upper limits, you want to go to the noise level. We don't have that. We are not there. There is an excess variance in this field. This is the NCP, the North Celestial Pole. But it's a huge improvement. This is just a figure that tells you what the power spectrum at K equal 0.08 H co-moving megaparsec inverse as a function of redshift for many, many experiments. The best results are from here. This is the HERA result, which they have published in 2022. It's still, or 23, I can't remember, 23, I think the last one. Since then, they haven't published because they hit the systematics. So they have crosstalk between instrument now, detectors now, and it's getting more difficult, so they have to understand that. These are our results. High redshifts, at high redshifts, there are a slew of results. And this is from NINOFAR. It's preliminary. We haven't published that, but we'll publish it soon. We are getting to ruling out actually the things that this is a model basically, and we are going down in terms of ruling out maybe even the I'll try the edges model. So this is the status of the field currently. However, we have, since then, we have kind of also submitted a paper on the 3C196 field. That's a different field. And there, this is 6 hours only. And we're already getting kind of results that are close to 140 hours of the 3C19, of the NCP. This is magnificent. I mean, 2 years ago, if you have told me that will be the result from this field, I wouldn't have believed you, because we didn't know how to calibrate that thing. Now we do. And this has been submitted, we have 1,000 hours there. The data is already there. We have 1,000 hours on this field and 1,500 hours on the other field. So the ability to detect stuff is there. We just need to figure out the systematics. This is very preliminary. Please don't quote this. This is after looking at these 6 hours and starting cleaning them up and adding kind of models for Torus A, which is kind of a nightmare in these things, these A-team things you have to model very, very carefully, and other issues like flagging CAS A and improving the analysis. This is the first time, and I'm very happy to report this. This is the first time where our upper limit sits on our noise. The first time. You see it. It's the orange thing sitting on the blue thing, which is marvelous. The dashed thing is the variance of the variance. This is the target. This is where we are. I mean, we are like all experiments when they start. We are looking for excess variance. Thing that is more than you expected, and you can attribute to the signal you're after. And this is 4.5 hours, because we throw some of these 6 hours away. We can return them back after we clean them. This is a different game now, and I'm very happy to say this. If I gave this a year ago, I would have been very pessimistic. I'm now maybe over-optimistic. I have to be realistic, and I once was asked by a journalist, what does it take to do this? I said, to do this, you have to be hopelessly optimistic, but brutally realistic. And this is this kind of game. We are getting there. Okay. There's lots of next steps. I will not go into the analysis. I just want to kind of flash this figure. So the analysis basically, let me go back. So the analysis basically, you see power spectra as a function of K, and these are models, and the dot is the red things are the data. So the more the data goes down, the more you rule out models. That's the game. Now, how you do this is complicated. Currently, what we do, we have cosmological simulations with sources. We predict power spectra, and those we compare with the measured power spectra. But then our statements are about the sources, this is what we can do now. The optimal thing is to do this, is to ask what are the parameters that decide the power spectrum in terms of the IgM itself, because this is what we are measuring. We are not measuring the sources, we are measuring the IgM, and compare that to the data. Most people, including us, doing the first one. We recently have started developing the second one. I'll stop almost now, so I'll skip all of this. This is just to show you that we have come up with a scheme to do this comparison between the power spectrum and the IgM, and it works marvelously well with completely independent simulation types. These are 3 independent simulations or tools of simulations. And you can see that we do well in all of them. So this parameterization that we have is working. We just need to understand it physically. It's like understanding the peaks in terms of the power spectrum and what each peak means, and etc. So we are in this game now. Okay, so we are getting there. I will not go through the details. The future is bright. If we get where we get, then SKA is around the corner. It started taking data 5 years, 6 years, within a decade, I think more realistically, we will start getting there. And lunar observatories are kind of sprouting everywhere, just because the governments are interested in the moon, and we are using that to go to the moon. Thank you very much, and sorry for taking a few minutes.
Okay, we went a little bit over time there, but I would like to pretend this is a panel discussion and have some discussion with the panel. Can we throw up the single slide before going to the audience? Because we kept more to time than the previous sessions. I don't know if there's a prize, but we win the prize. We, among us, tried to decide what are the main talking points, issues in this topic, and this is what we came up with. So, does somebody want to jump in and say something about the first one, or do we know enough about reionization, or could there be something very surprising still?
Well, go ahead.
I think, well, if you were asking this question before JWST, I would say no, but now I would say perhaps yes, because we see some things that are perhaps are small, some I don't like to call them tensions, but some disagreements between theory and data that are still small, but could point towards the fact that there is something missing. And clearly the fact that we are finding this excess of galaxies with respect to what we were assuming before JWST, I mean, then implies that reionization history must change with respect to what we previously know. So yes, I do expect surprises.
Yeah, I mean, I essentially agree. I mean, this plot of the ionization history has been plotted for a long time, that Andrea showed. But this is even before JWST, and everybody claimed that it's, we roughly understand how ionization proceeded. That's not true. There's another aspect to this which we have to consider, is that you look with JWST, you look at the tip of the iceberg. How that translates to ionizing the IgM is far from being understood. So the surprises might be in the sources, but also in the way the UV radiation spreads into the IgM. So I think the complementarity between the different probes is very important here. We probe the IgM as IgM, JWST probes the tip, and other telescopes probe the tip of the iceberg, and we have to kind of have a consistent and coherent picture at the end, and we are far from that.
No, just very quickly, galaxies, and in which abundance at Z25, and also all that bunch of AGN that were found that were not expected to be there. And, we always say, it's driven by galaxies, and then the last bit is done by AGN. Is this true? So, yeah, let's see how it evolves with new data, I guess, at this point.
Yeah, I mean, I was bravely arguing that maybe it's some other source, some other type of sources, like perhaps powered by black holes.
Okay, shall we move to that second point? So I think, when I first started doing cosmology, Gunn-Peterson stuff was everything. And then for the last 10, 15 years, the CMB has been setting the standard for what the epoch is. Are we past the CMB being the dominant constraint on reionization? Maybe that's a question for Marina.
Well, still the tightest constraint on tau comes from there. And, in the future, we mentioned Lightbird as a possibility to get from space the strongest constraint on tau yet. We are exploring within Lightbird the sensitivity on reionization history as well. And this will link to the next question that you rephrased in a way that seems that seems that you have suspicion on that, but I understand it's very. I'm talking about the KZ, no, exactly, no, and I understand that's complicated. It's complicated because there is a lot of interaction with other emission sources on those angular scales. And then even if you isolate KZ, which has got a special spectral signature with respect to the others, how can you disentangle homogeneous and patchy? Cross correlations there can play a role now that we are observing objects at the reionization epoch. That I don't know. Actually, that would be a nice thing to get.
What cross correlations?
Exactly, what cross correlation? I mean, KZ squared crosses some tracer squared, because otherwise you have the cancellation effects, but across what type of data, your data? Yes.
Yeah.
Lyman breaker. 21? No?
Well,
21?
Lyman alpha H0, I think it's good, but you can't go much beyond 9 or 10 when perhaps the discrepancy appears, right? And so it's okay. Maybe, well, for sure, 21 centimeters, you'd say, is the primary. Oh, absolutely. If you can see Lyman alpha emitters there, we only have 1 or 2, maybe.
Yeah, I mean, we checked the 21 centimeter cross correlation with the CMB, with the KZ. That's also difficult. I mean, that's very difficult, actually. Part of the problem is the integral nature of the KZ. And remember, 21 centimeter probes the regions that are neutral, whereas the KZ probes the regions that are ionized. And there is this silk damping effect that prevents us from going to the scales where this cross correlation is the most kind of prominent. So all of these things are important. I want to say a comment about the second point there, and the CMB tau. Again, tau is an integral measurement, and I think now there is some type of tension, although people kind of, whenever I ask it, they tend to kind of say that it's fine. There's indication from Lyman alpha systems that ionization didn't end at 6. There's still left over until very, very small redshift, even 5. People talk about 5.5, something like this. So on the one hand, tau tells us that the optical depth is very small. And we see the traces of this down to redshift 5.5, that not everything is ionized. On the other hand, you have JWST telling us we have these galaxies as early as 14, redshift 14, doing some stuff. And that's a bit of surprising, especially, I mean, naively you would think that the number of galaxies would increase exponentially. That's what Press-Schechter tells us, etc. And so we need a model that from redshift 14 to 6 to 8 doesn't do much, and suddenly kind of galaxies remember to form. I mean, it's just weird to me. Maybe there's a good answer.
but it seems like there is some misunderstanding there, or kind of lack of understanding of the
No, I see your point, and it's also clearly surprising. It's important, though, that we, you have to play around with escape fraction, that term that essentially tunes the amount of photons that escape from the galaxy. And on that end, the perspectives are also good, because now with JWST, we are measuring the spectra of distant galaxies, and therefore we can exactly determine, many parameters that enter the escape fraction, which perhaps in a statistical way can now become more and more solid. So I'm positive about that.
Okay, let's try to, we're doing well here for time, but let's try to go to the last question. And I apologize looking at this slide that I made this S small in KSZ, and that's not to, right? That's not because I think the S contribution was small. Apologies, Rashid. Can we go to the last question? Maybe we'll start with Marina, since she didn't speak in the last question. What do you think the next big thing is that we're going to learn about reionization? What's coming?
Difficult to say. Well, difficult to say. That's a very complicated question. Breakthrough, although I would have not expected from, our side, let's say our side, we can have a solid constraint, I see. Solid constraint indicating late and fast at the moment. But I'm curious to see how it all evolves in the front of Euclid, JWST, what they can say,
But are we going to get a second parameter from the CMB, or is that too unrealistic?
What do you mean by a second?
Tau plus something,
Tau plus
the width or something.
Difficult to say.
Yeah.
It doesn't seem to be wanted,
Salim or Andrea?
Well, maybe I think we can certainly expect breakthroughs. Well, certainly from 21 centimeter, that would be fantastic if we can manage to deal with the systematics. But also the fact that there's something also that puzzles me, and going back to what Eiichiro was asking before, that in spite of the fact that the universe supposedly at redshift larger than 10 was totally neutral, we have 2 or 3 Lyman alpha emitters there. So you see Lyman alpha from objects that are we should not see it, because they should be totally scattered off the line of sight by the neutral gas. So it implies, that perhaps suggests, that the universe was not completely neutral, even at redshift 10. And so that's why I was asking yesterday whether there is a way to shrink the errors, because right now all these models pass through the uncertainty in the Planck tau e. But if you can shrink that, it would be great. So
0.002. That's your target if you are looking only from CMB side. So that's your target.
I enjoy how the outside world's reminding us that background noise is a difficult experimental thing to cope with. Salim, last word.
So, I wish it's the 21 centimeter, but that's my hope. But I should say that I have been very positively surprised by the Lyman alpha forest kind of results, the troughs. I mean, it has been, most of the progress actually has been coming from there in the last, at least in the redshift 5.5 to 6 or 7 range. So that's one very good avenue. I think we heard about the spherics, and so line intensity mapping, that might be very promising as well. We really don't know. But whatever it is, it should be consistent with the other things, and currently it's a mess, I guess. Thank you.
Let's throw it open to the audience now. We still have time. So am I supposed to go with the microphone, or does somebody else do that? Yeah.
Thanks a lot. Thanks a lot for the presentations and for the panel discussions. I have a comment and a question. So the comment is about the first point. Aren't we in a situation where basically the let's say, to put it provocatively, oversimplified models of the ionization are facing reality of the sky with the observations. And my question is, I think that we've been discussing a lot about the hydrogen reionization, but there is a second one, which is the helium. And I was wondering, and this is maybe targeted to Andrea, how would the constraints on the helium reionization fit with respect to the discoveries of potential very high redshift galaxies?
Well, thank you. They are both important questions, obviously. Well, I wouldn't say that all the reionization models are all simplified. At least they are sufficiently complex to explain the complexity of the data, given that different experiments, because there are different ways to obtain the neutral hydrogen fraction, different type of experiments. You can use the damping wing of galaxies, the damping wing of quasars.
No, sorry, it was not about the reionization models. I didn't make it clear. The formation of structures, star formation, galaxy formation, stochastic star formation, and all these things.
Yeah,
sorry.
but these are part of the model in the sense that you have to include the sources that you think are important. Now we are finding out that stars perhaps have trouble in starting their ionization because there are sources that we cannot explain. And so in that sense, I think that I'm not worried about particularly about the complexity, the lack of complexity of the models or the lack of physics. I think that's more or less sufficient, unless we are missing something very important. I was mentioning before primordial black holes, that these are not included at the moment in any essentially of the models. Coming back to your second point, is that the helium, this helium can provide constraints because you can't have helium reionization occurring too early on. We have constraints on that, and that means that you can't put too many AGNs at early epochs. But now all the quasars or AGNs, faint AGNs that JWST is finding, apparently do not have any X-ray emissions. That is also puzzling. Maybe they don't have a corona or maybe something else, but they don't have emissions. So you can also hide that ionization with different sources.
There were lots of hands went up. I don't know who was next, but let's go to Dick, because I don't think he's asked a question yet, has he?
Well, I want to speak to the future of line intensity.
I'm sorry, can you speak high? Because here there is some effect from the noise outside is very hard.
It's noise. It's what
noise.
we need to figure out. Line intensity mapping is a tremendous future from my point of view. We're going to pave this, hopefully, we will pave the sky with all sorts of lines, and of course we've heard some of this today, but the problem is the medium is incredibly complex. And to think that you can nail it with the hydro, certainly not the hydro now, I mean, we're into the depths of this and use response functions and all of that, but the formation of the galaxies, whether they're little galaxies or bigger galaxies, are incredibly complicated, especially if you start to look for the different elements. So we have a big history with trying to do CO, which is probably one of the hardest to go after, but C2 is non-trivial. H2 is actually non-trivial, and they're different parts of the galaxy, and they're all playing off of each other with all sorts of energetic feedback. And so to think that we are close, and this goes to Nabila's point, we are close to be able to nail any of this is kind of fantasy. That doesn't mean that we can stop doing it. We have no choice. If we're going to follow this route, we have to incrementally try and improve the hydro and have feedback with the few results that we get. But we also have to be a little bit modest in, what tends to happen is people say, my sim is better than everybody else's and I've got cosmic truth. That is not going to be the case probably for decades. The thing that we have to pay attention to, for example, is the extreme importance of magnetic fields and cosmic rays in the first generation of objects, and that those can do a huge amount of feedback. And I'm not even talking about, the ionizing radiation, which is, blowing things apart at short scales, etc. I'm talking about, the fundamental physics aspects, because you get these if you're doing black hole formation, you get dynamos. And the dynamos are creating the magnetic fields, and the magnetic fields are modifying the medium, and that's changing all of the star formation. So it's a game that we're going to be playing for a very long time, and it's worthwhile to do, but modesty is something that should be injected into our community. I'm directing this to you. Not because you're not modest, but just because you play the game.
Not taking it personally, don't worry. But clearly, no, you made an important point. I mean, I agree that intensity mapping, it's important. I think that it will not be, unfortunately, sensitive to anything that happens beyond redshift 10. It will be very hard if you are talking about carbon-2 intensity mapping or other lines like the ones you mentioned. But apart from that, you mentioned the point about magnetic fields, which I think has been overlooked, even though there are experts that work on putting limits from the CMB on the intensity of primordial magnetic fields. And so the limits that we have so far, even the recent detections at lower redshift through Faraday rotation, they seem to imply that the intensity of the magnetic field, there's an upper limit which is, if I'm not wrong, is 10 to the minus 9 Gauss, and therefore I'm not sure that they must be there, but they may not be dynamically important. But that's, yeah, maybe you can have some sort of dynamo, sure, locally it could become important. So these are all things that we don't know. Yeah.
Can I say something about this? So I agree with the comment that it's very difficult. H1 is the example of that. We've thought it's, but I would like to separate two things. In the H1, for example, which was the situation of the CMB before COBE, we would be happy with a detection that we think has anything to do with cosmology or the real world. The interpretation will come later, and I think in many of these experiments, just detecting something is quite an achievement. What it means in terms of what the physics of the galaxy formation, of cosmology, of anything, that's the next step. So at least in H1, which is the most advanced, I think, from these line intensity mapping modeling kind of things, I would be happy with the detection. What it means, okay, there are many other generations that can do that, but for the time being, we would like to see a defect. And this is actually what happened with COBE, if you go back to the history. What we learned from COBE about cosmological models, except that it's just delta T, delta T over T is 10 to minus 5. Other than the face of God, yes.
Let's move on to the next. I think Ruth hasn't asked a question yet.
Yeah, I have a question to you, Salem, about 21 centimeter, not to do with reionization, but at lower redshift there is Mercat who they have like 2 papers, I think, preprints, where they say they have discovered the 21 centimeter spectrum. What do you say to this?
Right.
Preprint?
So that's a very good question. It has nothing to do with the ionization. This is the leftover H1 at lower redshifts. So that's to start with. And I think that's a very promising avenue to all kinds of things. I would love to get my hands on the Mercat data. You can imagine, for instance, probing filaments with this type of thing. Just looking at stacking filaments and ask how much ionized neutral stuff we have. So they are doing a very good job, and currently I think CHIME has the same thing, is this cross correlation with known structures and that you can detect. If we get to the situation where we detect things on their own right, H1, that tells us a lot about UV radiation at lower redshifts. That tells us a lot of things. So this is a very promising avenue, right? Radio astronomy is developing a lot in these types of directions, but we are not there yet. We are getting close, but that's a very promising avenue.
The CHIME people tell me they're very close, but they've told me that for the last... Yunji.
I have 2 questions. One is to Marina, that you mentioned about this homogeneous KIZ and also patchy reionization KIZ. And the patchy one is highly nonlinear and non-Gaussian. And therefore, to constrain tau by using KIZ, you need to have a reasonable model for the patchy part, and how do you deal with that?
Well, I guess people have been working on simulation of increasing complexity on this. How representative are those? There are several of these, and I think on simulations is the way they do it.
Okay. The other question to Salim, that yesterday we heard about this interesting Sphere X experiment, which may also measure high redshift galaxy. And in terms of the cost correlation, can you comment on some of the prospect of using Sphere X?
Yeah, I mean, again, we have to understand what Sphere X is exactly measuring, what we are measuring. But in the last 20 years, because we didn't have results from the data, we also did some theoretical predictions of cross-correlating everything with everything. And that's, yeah, and I think that's a very important avenue to pursue. So we're doing that. We plan to do it also for with Lyman alpha emitters, as I mentioned, with the CMB, with all kinds of things. I think this is a very important aspect of the game that we should pursue further.
Okay, Jens is desperate to ask a question, so we can all guess what the subject is.
Maybe. It's a question to Salim. So you mentioned the importance of the CMB temperature and the brightness fluctuations in the equation, and you also mentioned in connection with edges uncertainties, of course, in the radio flux in principle. So uncertainties in the prediction driven by the injection processes at high energies, that's one of the astrophysical sources we normally think about. But what about the radio flux generated, you know, the fluctuations in the radio and really the basically brightness of the background temperature to which we are doing the contrast? What's your perspective?
So that's another important aspect. And I mean, if we have some of the models that people have tried to constrain with the edges have to do with this. For instance, in the HERA paper, which goes back down, they looked actually at this, whether, you know, with radio background or without radio background. We do the same thing with LOFAR data. We add radio background or no radio background. I don't think we are currently in a situation where we can, at the lower redshifts, where we can say something definite about this. Seems that we can get by without it. But if there are early sources that might be interesting, I mean, you know, but one of the things that you know that people have known for a while, if you look at high redshift quasars, very few of them are radio loud. Some, I mean, I don't know the physics, but understand it actually. But there seems to be something different at these high redshifts than low redshifts in terms of this population. So which is interesting. But yeah, that's my answer to you.
Okay, let me give an opportunity for anybody who hasn't asked a question who is desperate to do so. Is there any takers? Otherwise, lunch is apparently in the back and waiting, calling to us.
Rashid.
Oh, Rashid, good. Last word for Professor Sunyev.
I think maybe first word during this conversation. I am amused that we are still speaking about 21 centimeter tomography and so on, when now these new discoveries of galaxies at redshift 10, 14 show us that there should be enormous amount of carbon monoxide, just carbon, other molecular lights. And these molecular lights shifted from redshift 10 are much more easier to observe than hydrogen lights. Just these are permitted transitions and not totally forbidden transitions like 21 centimeter. And we should observe these bright lines because in our galaxy today, in very difficult millimeter band, people are observing and enjoying a lot of new discoveries with carbon monoxide, for example. If we go to redshift 10, all these beautiful physics, all these lines are moving to the excellent and well, how to say, developed spectral bands. And I think people like Jose Alberto, for example, they should think today how to use their new instruments, which are very good in the band of several tens of gigahertz, for example, or in gigahertz band, where there are huge antennae, new antennae will come. And it is absolutely important not to forget about these lines. I tried myself to make estimates maybe 20 years ago, but now with these new discoveries, it's becoming absolutely necessary to forget about the classical thing, even about Thomson scattering, which is KZ. You understand me? You are coming to the great atomic physics, molecular physics, which is all transitions are permitted. This is enormously important. Please do not forget, and first new simulation should include these lines, because we are observing lines in the spectra of these galaxies.
Yep.
I am not requesting that you will observe in optics redshifted the lines of carbon and so on, but in molecular lines should be observed.
Just if I can reply, I think that Rashid, there's a good news that from the galaxy redshift 14 and another one at redshift 12.3, we have detected the forbidden oxygen 388 micron line from the galaxy. So it's a detection, so it's amazing. We didn't detect carbon 2, we could, I mean, we have an upper limit, but yeah, but it's there because they are all evolved and they have, emission lines that can be detected by ALMA.
So
Okay.
I have one comment.
Salim.
It's impossible not to agree with you, Rashid. So that's the first thing. But I would also caution that these are, about how diffuse are these lines. Each one is really the IGM. The rest are more galaxies. So there is place for both. And we absolutely should pursue what you are suggesting.
Okay, with that, I think we should move to lunch, but we should thank all the panelists again for their contributions.
And the chairman.
Yeah. Thanks.